Okay, then let's get started. So last time we talked about VAEs and elbow variational inference, and today we're going to talk about other generative models. So in the previous lecture, we said directly maximizing the log likelihood was hard under our modeling choices. So we ended up optimizing the lower bound instead. We sample a mini batch of data, compute the elbow, maximize elbow, right? That changes our parameters theta and phi. And then resample a mini batch of clean data X, re-evaluate elbow, maximize elbow with respect to encoder, decoder parameters, theta and phi, and repeat. So today we'll talk about autoregressive models that exactly maximize the likelihood, but has very slow sampling procedure. And exact because we're going to model our generative process that way. And then we're going to talk about generative adversarial networks, GANs, where here we don't care about the likelihood. We just care about what's called implicit density, and has very fast sampling, just as VAEs. So once again, autoregressive models, we want to do explicit likelihood maximization. GAN, we want to do implicitly. So here's one page summary contrasting these three different generative models. In VAEs, under our model, this data likelihood was intractable because it involved integral over all possible combination of the latent variable Z. And this guy had nonlinearities. So this is a neural network, has SILU, ReLU, etc., which is not analytically integrable. So we ended up maximizing the lower bound. And once we finished training, sampling was fast. We sampled some IID, easy to sample distribution, then pass it through the decoder for one-shot generation. Autoregressive models, they use probability chain rule to model the data likelihood. And this is easy to maximize directly, but generating samples is very slow. You have to generate one token at a time or one pixel at a time. GANs, we don't bother evaluating p theta of x, but instead we formulate it as a two-player game between two players, adversarial players, generator and discriminator. And here, generation is also fast. You just sample some random vector from some easy to sample distribution and turn it into an image or whatever you want. So let's first talk about autoregressive models like pixel RNN, pixel CNN. So here, the idea is to model the distribution using the probability chain rule. So given any ordered random variable x1 through xt, the chain rule gives us the simple breakdown, p of x. The joint distribution of data is p of x1 times p of x2 given x1, x3 given x1, x2, and so forth. So we can compactly write it in this notation. It's basically product of p of xt given all is past, right? This holds no matter what. This is just probability. So here the idea is to choose an ordering and train a neural network to predict next variable given all the previous variables. Okay, so we're going to just parameterize this guy. So let's take it more concretely. So for an image generation task, we're going to have flat pixels flattened pixels in a raster scan order. This means if you have an image, so let's just say channel size is 1 for simplicity. Raster scan goes row major format typically. Like this. So this is going to be your order of the random variables. x1, x2, blah, blah, blah. X, I guess, w plus 1, blah, blah, blah. Okay, so we define the ordering between the random variables, and the random variable here represents what is the range of the random variable. It's for a uint A image, 0 and 255 integer. Okay, to make it explicit, dot, dot, dot. Okay, so probability chain rule, and we're gonna model our conditional distribution using p theta. This is gonna be our parameterized neural network, which tries to put probability distribution on the pixel value of the corresponding teeth pixel given all is passed. So we have the training data available. So given, let's say we're looking at distribution here, right? So given all its past information, this enters here with condition on the past, and we're going to have a probability distribution on possible values of xt, 0, 1, 2, all the way to 255. Okay? So the task is simple. We want to maximize the log likelihood. How do we define the log likelihood? Sum of the log of probability associated with xt given all its past. So this model gives us an exact likelihood, unlike VAEs and GANs. So what's nice about this is we can exactly optimize what we want, basically. So the training objective is directly aligned with what we want. And what else? What's good about it if we can exactly evaluate the likelihood? Anything good during inference? So let's contrast this to VAE. So let's say we take a trained VAE and trained our regressive image model, okay, and we generate images using VAE and one using our regressive model. So what's the utility of having access to exact likelihood? What benefit do we have? So the question is, you sample Z from PZ, pass it through VAE decoder, generate XZ. And then here you auto-regressively generate one pixel at a time, generate this guy, given this guy, generate this guy, given these two, generate this guy one at a time, and you generate image 1. So that's image 1 and image 2. What's the utility of having access to this this likelihood? That's also true. You can use top K or top P because you have access to P theta of X. What else? So he said something like, you can use this guy to evaluate whether this is fake or real. More generally, the answer I was looking for was, you can use this to self-evaluate the quality of generated images. So you generate an image, you now have log p theta of x hat 2. You have a single number indicating the quality of the generated image. So this is a powerful tool because you can now evaluate the generated quality. Here, you cannot evaluate your quality. So maybe you can do something like rejection sampling based on the output here. Okay, so how does it work more specifically? So pixels are ordered row by row in a raster scan ordering, and to generate current pixel xt, you condition on all the previously generated pixels. So previous is defined by the prefixed ordering among the random variables. So we decided to go raster scan. So everything previous is all these guys here. So previous pixels are above or to the left of the raster order. So data likelihood is basically p of xij given all is passed. Okay, so how about color images? So you have 3 channels, red, green, blue channel. So channel size now is 3. So the idea is the same. So you just need to fix an ordering among these channels. So specifically, let's just say we chose red comes first, then comes green, and comes blue. So we can do something like this. So to generate the red pixel value for location I, condition on all the past. And to generate the green value for the ith pixel, you condition on all the past, and also condition on what you just generated here. And to generate the blue pixel, all the past, the red pixel value you just generated 2 steps ago, and the green pixel value you just generated. Okay. So this ordering is arbitrary, but you must use a fixed ordering. So how do we train this? Very simple. You just need to maximize the exact likelihood. And using the probability chain rule, we're going to just condition on all the past. So this is just a supervised learning, right? Given all the previous information, you predict the next pixel. So what kind of modeling distribution are we going to use? For example, for unit 8 images, this is going to be integer values. So we might as well just use categorical distribution. Right? So we have discrete choices 1, 0, 1, all the way to 255. And we have a categorical distribution. Right? So just matrix multiply where the out dimension is 256. Right? Okay, so once we finish training, how do we sample or how do we do inference? So we must follow the specific order that we chose. So we must sequentially generate 1 pixel at a time. So generate x1. Given x1, generate x2. Given x1, x2, generate X3, and so forth. So the trade-off is autoregressive models have exact likelihood, which is good, and stable training. It's just supervised learning. But the generation is so slow because we have to generate one pixel at a time, and it's impossible to parallelize this. Right? No parallelization among pixels. Okay. So one alternative is called pixel CNN. Here, what you want to do is, so two different ways to implement this would be pixel RNN versus pixel CNN. So use RNN as a backbone model and use recurrent connections across image positions. And you could also do CNN as the backbone model. And here you want to use the masked convolution. We'll see a picture what this is. But obviously, during training, you want to prevent the model from seeing the past, right? So you want to mask the convolution so you only see your predecessor random variables. But what's nice about pixel CNN is you can parallelize this during training. But what's the trade-off? Here, you now break this equality here. Because since you're going to use fixed size convolution kernel with fixed size height and width kernel, here you're going to have to, clip how many variables you see. Right? Say your kernel size at a convolution window is h by h. Here you're going to see at most h squared pixels. So here, we're not going to have exact likelihood anymore in pixel CNN. So at least the training can be done in parallel, but sampling inference, still no hope. You have to generate one pixel at a time. So what's pixel CNN? So you have convolutional neural network as a backbone model. So normally, if this is your center of focus in a convolution, and you apply a convolution window like this, you have access to everything in the field of view. And we want to explicitly block out this component here. So you have to apply a mask so that the convolution window completely multiplies whatever input it receives to 0 at this location, because we don't want it to see the future information. Because during inference, we cannot see the future. We can only condition on what we generated. So that's going to be our masked convolution. And the trade-off, an important thing to notice is here we only have access to this many context. So to generate xt, to be mathematically correct, you will have to condition on everything. But we cannot because we're restricted to this h by h, w by h convolution kernel, right? So there could be something outside here, outside the convolution window, but we don't have access to it anymore because we're going to use a fixed size convolution kernel. That's good and bad. That's good because we can parallelize the training process. It's bad because we no longer have exact likelihood. Okay? So how does it work in implementation? In the very first layer of CNN, this would be your mask. So here, let's say you want to generate the center pixel. You don't have access to yourself because to prevent cheating, you have nothing to condition on here in the very first layer of CNN. Right? You only have access to the past information, these guys. From the second layer and on, you have something to condition on, which is whatever the first layer outputted. So yes, you still cannot see the future pixels, but you can use the current position hidden features from whatever the first layer outputs. So you use two different sets of masks for pixel CNN. Does this make sense? Okay. Yeah, so like I said, the training is parallel because now we have broken the temporal dependency by using a fixed size convolution kernel. So for every single location, you just need to condition on whatever the convolution kernel can see. Whatever's outside the convolution kernel, you don't care. You're going to drop the dependency. So during training, pixel CNN training can be done in parallel over all pixel locations, which is extremely fast. But for sampling, unfortunately, you need to see the context for the convolution kernel, so you have to do one by one generation of the pixels. So it's going to be slow. So let's do a brief summary. So you could do RNN or CNN as the backbone model, and at least you can parallelize the training if you do pixel CNN. But okay, so here this is not exact. Sorry, I'm going to fix this. So weakness is it has bounded receptive field unless deep or dilated. So this means if we, this is similar to the sliding window attention thing we talked about. I don't know if you still remember in LLMs. If you stack the CNN layers very, very deep, you can propagate the field of view to the later layers, right? So you can have more effective, larger field of view for the later layers. So if you stack it really, really deep, yes, you can be exact, but still, mathematically, this is not exact equality here because we're gonna clip how many past pixels you can see. All right, so that's it for our regressive models, and let's talk about generative adversarial networks. This used to be very, very famous in 2014, 15, 16, but diffusion models have taken over, and we'll get there, yes, but the underlying mathematical tools are interesting, and you might, who knows, maybe this will come back and beat diffusion models. Okay, so when GAN came out, the generative quality had a huge jump in a positive way compared to VAEs, because we were now able to see really crisp edges in the generated images. So now, as opposed to probabilistic view, we're going to take a game theoretic point of view of how we play this game of image generation. So we're going to completely switch gears and set aside our probability for now, and just purely let's just look at it in terms of game theory and optimization. So the idea is we're going to sample Z from easy to sample distributions like uniform or IID, a standard normal distribution, pass it through the generator, and it's going to create some fake samples. So when I say fake versus real, fake means whatever the network generated. Real means the data sampled directly from the data distribution. So here, we're going to not try to bother coming up with a tractable formula for big data of X. So we're not going to directly or indirectly try to maximize the likelihood. So we're going to formulate it as a two-player game. So who are the players here? There's generator and discriminator. These are opposite sides. They compete against each other on the same objective. So the generator tries to produce fake samples that look real. Discriminator is a classifier, is a binary classifier. It tries to distinguish real from fake. So they try to discriminate. So it tries to estimate, given some data X, probability of real. So y equals 1 means real, 0 means fake. So generator generates image, and discriminator tries to discriminate whether it's fake or real. So here is a flow. You sample sample Z from easy to sample distribution, pass it to the generator here, generates some fake data. And discriminator, without knowing, will receive either fake or real data and tries to gauge whether it was real or fake. So discriminator will want to be a good classifier. Generator will try to fool the discriminator into thinking the fake is real. So the analogy is discriminator is a police officer, and generator is a criminal who wants to print fake money. So generator wants to create fake money that looks as real as possible so that it can fool the police officer. And police officer will try its best to distinguish whether it's a printed money or real money. So here's the minimax objective. So they share the same objective, but generator wants to minimize and discriminator wants to maximize. So the objective function looks like this. So it's a function of G and D, where these are individual neural networks. So when data is sampled from the real distribution, the discriminator wants to maximize this, and makes sense, right? D of X is supposed to be P Y is 1 given X, or P real given X. Right? When the data is sampled from the true data distribution, discriminator wants to increase this. On the other hand, if data is sampled from the fake distribution, gets passed as input to the generator, discriminator wants to maximize, so it's log of 1 minus that. So discriminator wants to send it to 0. Make sense? So when the data is sampled from real distribution, it wants to send this guy to 1. And when the sample is generated from the fake distribution and it's indeed fake, it's advantageous for the discriminator to output 0. How about the generator? The first term does not depend on the generator, so we only need to look at the second term. So since the generator wants to minimize, it wants to make this go to 1, so it wants to fool the discriminator into thinking fake is real. Okay, so how do we do updates or training? So you now take turns. So here you first update the discriminator. So discriminator appears both in the first term and second term. So you want to do gradient ascent for k amount of steps on the discriminator parameter. And then you want to update the generator. So you take the second term and minimize, so gradient descent on the generator parameters, and repeat. So how many update steps for discriminator versus how many updates for generator? That's black magic. You have to try various trial and error and find out something that works. But in terms of the optimization perspective, this is very, very hard problem because it's very easy to get stuck in a local optimum because this is a minimax objective. You want to do gradient ascent here and you want to do gradient descent here. So optimization can be difficult. And the problem is, so there are many problems, but one problem that's known is this generator loss can saturate when discriminator is too good. So especially early on in the training, when the generated image looks really, really bad, it's easy for the discriminator to discriminate. So in this case, it's very hard to escape from local optimum. So we don't want discriminator to get too good too early. Why? Because of this. So let's look at the original minimax generator loss. You want to minimize log of 1 minus discriminator output of the generated image. So let's compare this objective with this objective. Okay, so we had log 1 minus d of g of z. Now we're going to look at minus log d g z. Let's compare this guy to this guy. Okay, log monotone. Don't worry about it. 1 is just constant. So we took this guy outside. And let's look at how the gradient is going to behave. So initially, early on in the training, this is going to be random and garbage. Right? Generator is randomly initialized, so the generated image it's going to look garbage. So it's going to be very easy for the discriminator to discriminate. So before, if you look at the blue curve, when this guy discriminator is too good and output is 0, okay, this is fake. Gradient is going to be very flat. So it's going to be difficult to change the parameters for the generator. I want to draw a clean tangent. Okay. Let's compare that with after changing the loss. Okay, here, gradient is very steep, so it's going to be easier to do gradient descent on the generator parameters. Compare this to this. So we changed the saturating objective to non-saturating objective, which is going to help us a lot, especially during the earlier stages of training when the generated image quality is garbage. But still, in terms of, so the important thing is you want to decrease this. So instead of decreasing this, we're going to just decrease this. The more important thing is the direction in which we influence the generator parameters. So log 1 minus that versus negative log. Not so much change. But mathematically, we motivated from the two-player objective and getting rid of this guy, taking this guy outside. Sounds like a hack. So there are some theoretical justifications for why this is a better formula, but in the interest of the scope of the undergrad class, I'm gonna not go too much into the theory. So here's the pseudocode algorithm. So you alternate between the discriminator update and generator update. So you sample the real mini-batch from P data, you sample noise from PZ, and you pass it through the generator and create some fake images. And since the discriminator appears in the first and second term, you maximize this. So this means gradient ascent on D parameters for k steps. And then for generator update, you only need to worry about the first term. This second term here. So you just need to sample the mini batch of the random noise, create some fake data, and just work with this guy. So, well, same thing. You can do gradient ascent here, gradient descent here. So here, gradient ascent on D and G. Sorry, on G. For, I don't know, H steps. How many steps? Black magic. Learning rate for discriminator versus generator, black magic as well. But the important thing is we don't want the discriminator to get too good too early. So you don't want an aggressive learning rate for the discriminator, because if the discriminator gets too good too early, then generator just gives up, just outputs something close to random noise and optimization doesn't go anywhere. So you want to slowly update discriminator and give enough chance for the generator to catch up. Because this is much more difficult task if you think about it. Discriminator output is two-dimensional. Or to be exact, one-dimensional. It just outputs probability, whether it's fake or real. But this guy has to output H by W by C full-size image, so it has much more parameters, and it's a very difficult task to generate an image that looks real. So you don't want to update this guy very aggressively. So after training, you throw away the discriminator and you sample Z from your sampling distribution, pass it to the generator, and that's your sample. So sampling is fast, just as fast as VAEs. Just do a single forward pass through the generator. Okay, so that's the algorithm, and it was very simple. Looked simple, right? So the black magic is here. To make it work, you have to tune this guy, learning rate for D, learning rate for G, and hopefully something will work. If it works, it generates really, really clean images. If it doesn't, it's going to just give up here and not learn anything. Okay, so let's analyze it more theoretically. So let's go back to the JSD from 2 lectures ago. So Jensen-Shannon divergence between two probability distributions P and Q is 1/2 the KL of the average distribution plus 1/2 the KL of Q versus M. And what's nice about it is it's symmetric, unlike KL divergence. So if you swap the ordering, it doesn't matter, because we constructed it that way. And it's really nice because it's bounded. KL divergence is not bounded above. So with log base 2, it's bounded above by log of 2. Sorry, yeah, I got confused. So with log base 2, it's upper bounded by 1. With natural log, it's upper bounded by log of 2. Okay, so it's bounded. And let's first think about the optimal discriminator for a fixed generator. So just to introduce the notation, PG stands for the fake samples. So sampling Z from some distribution, passing it through the generator, and this distribution on the fake images, let's call it P of G. So again, fixed generator. We're trying to figure out, for a fixed generator, what is the optimal discriminator. So fixed generator, discriminator maximizes the shared objective. And the proposition is, for fixed generator, the optimal generator is P data of X over P data of X plus PG of X. Okay, why? Okay, so for a fixed generator, I'm going to rewrite the objective, this guy, as integral. So I'm going to expand the expectation sign. So that's why we have the integrals and the distributions here. And this can be optimized point-wise for each x. So let's just, to make it easy, let's just give it some name. So this, I'm going to call it A. This, I'm going to call it B. D of X, I'm going to call it Y. So we're maximizing A log Y plus B log 1 minus Y. So let's take the derivative and solve for Y. That's equal to A over A plus B. So the optimal discriminator, given a fixed generator G of X, is P data of X over P data of X plus PG of X. So what does this mean? What's the meaning of the proposition? So what if the generator is perfect? What happens then? So we worked out the analytic form of optimal discriminator for whatever some fixed G. So what if G is perfect? Can you speak up? And then what happens? Right, right. So if the generator is perfect, the optimal discriminator is going to be 1/2. Why? Because P data, PG is going to be the same. So this, if their distributions match exactly, then that's the perfect generator. Then in that case, the optimal discriminator is going to output 1/2. For perfect generator. Okay, so yeah, I'm going to skip this slide. Okay, so now let's plug our optimal discriminator back into our objective and look at it in terms of the generator optimization. So we worked out for a fixed generator, the optimal discriminator is following. So in the objective, the remaining variable is G, the generator. So let's plug in the optimal discriminator into the equation. So we got this formula here. Look familiar? So let's go back. So JSD is KL between P and M and Q and M. M is the average distribution. So you guys work out the math. So definition of KL we talked about, and it's easy to realize that if you plug in definition of KL here and here, it's going to be negative log 4 plus 2 times JSD of two distributions, P data and PG, real distribution and fake distribution. Okay, so now we worked out this much. In terms of the generator, if you plug in the optimal discriminator, that's negative 4 plus 2 times JSD between real distribution and fake distribution. And we know JSD is bounded between 0 and 1. And remember, generator wants to minimize. So in order to achieve global minimum, it's achieved when JSD is 0. And JSD is 0 by property of KL if and only if the two distributions are identical. So that means at optimality, discriminator outputs 1/2. So it's completely confused. So remember, this outputs P of real given X. That's 0.5. It's completely confused. And the objective equals to negative log 4 because JSD became 0. Meaning the fake data distribution completely mimics the true data distribution. So the meaning is if the generated distribution equals the data distribution, the discriminator cannot distinguish real from fake. And the objective value is going to be negative log 4. So what's nice about it is, okay, the optimization is very, very difficult because of mean and max, but at least we can monitor the progress to go. Because we know where the end goal is in terms of the objective, so we can gauge how far we are off from the objective. Not just looking at random generated images, we can mathematically gauge how far we are off in terms of the objective. Because almost all optimization problems that we discussed so far, we don't know what the true optimum is. We just, in most cases, this is iteration t, some function of t, and looks something like this. Okay, it looks to go down. All right, good. That's how we do it, because we don't know what the end result is. But here, at least we know. Okay, all right. If we're done, we should see this value here. That's the lower bound. Okay, so what are some failure modes? Has some vanishing gradients problem. We talked about this. So when discriminator becomes too good too early, generator just completely gives up and converges to local optimum. And what's known is it tries to do mode collapse. So when the data distribution is multimodal, it tries to lock on to one of the modes. This is good and bad. So VAE tries to do different. It tries to, fit as much data as possible under the model. But GANs tries to lock on to a mode, which can be good because you can generate very high quality samples. And the dynamics is very difficult to optimize because you have two guys trying to compete against each other. And if you're interested in this line of work, there's deep theory why this might be a good idea. So Wasserstein GANs try to analyze this in terms of Wasserstein distance between two distributions. And there are many different architectural knowledge and normalization, gradient penalties, and landscapes. So here are some generated samples. So to the left here, these are all generated. The quality looks good. And this is the nearest neighbor from the training set. So it looks almost indistinguishable to me. And same thing for the faces. And Cypher, I don't know, doesn't look very good. It's probably because the training data is so... Yeah, this is the actual training data. So, and in order to make this work meaning to generate high quality, high resolution images, you need to upsample whatever the generator outputs. So this is the architectural choice for the generator. So you need to go from low dimensional vector to a high dimensional object. So this is completely different from what we just talked about. So this is the architecture inside the generator. So how do we go from low to high resolution? So you need to learn how to upsample the input. So this is called transposed convolution or fractional striated convolution. So blue maps are inputs. So you first upsample. Let's say you have 2x2 image. You create spacings apart from each other, right? You first upsample, and this is going to be your output. Given this as input, this input, upsample the input, this output. You apply convolution on the upsampled input. That's your transposed convolution. This is how you increase the resolution from low to high. So in animation, it looks like this. So here, there's a link here where you can click and look at the animation. So here, to generate this output, it's going to be whatever the convolution kernel, inner product, this slice here, this matrix, I don't know, let's call it X. That's the output here. And you move on, so generate the second input, you apply convolution on this fragment here, and you move on to the third pixel, apply convolution here, and so forth. And if you want to generate 2x resolution, you do the same thing. You create upsampled image. So plug in, you increase the size, plug in zeros here, and then apply the same procedure. This is how you keep increasing resolution twice at each convolution layer. So this is the deep convolutional GAN, or DC GAN. So they made lots of architectural guidelines for stable generation. So the key component is what we just saw, transpose convolutions in the generator. And they use batch norm and remove fully connected layers, and use value in the generator except 10H at the output, and use leaky value in the discriminator. And this is the architecture. So you take as input 100-dimensional random vector as input, and you increase the spatial resolutions from 4, 8, 16, 32, 64. And for the low resolution, you compensate by increasing the channel size, and you keep decreasing the channel size as you go down, as you increase the spatial resolution. So that means here, the channel goes down over layers. Channel size goes down, but height and width increases 2x. This decreased by half to compensate. So this is the generated images for the room interior data set. I don't know the exact naming for the data set, but at that time in 2016, this was revolutionary because all we saw from VAEs were very, very blurry images, but this was, I think, the first model that outputted very crisp edges and something that looked really realistic. And you can do the same thing, interpolation in the latent dimensions. So we talked about latent traversals last time. So you can do the same thing. So when you sample Z, you can do you can walk traversals in the latent space and generate and see how the room changes. I don't know, there's I guess a lighting here and a sofa. It turns into a bed naturally, and something like this. And you can do latent space arithmetic as well. So you sample some Z's from the model and collect the Z's that output smiling woman, and average the Z's that output smiling woman, and you sample Z's that output neutral woman, sample the Z's, average the Z's in the Z space. So if you subtract the two and add in the Z's for the neutral men, you can, and you could push the Z into the generator. It outputs smiling men. Something like this happens in GANs as well. So linear operations in the latent space corresponds to interpretable image changes. Same thing. This is a funny one. So you collect the Z's that output glasses, men with glasses, subtract the Z's that output men with no glasses, add in the Z's that output no glasses woman, and you pass it to the generator and do latent traversal. You get woman with glasses. Okay, so let's do a summary of the generated models. So we talked about VAEs, autoregressive models, and GANs. And VAE's density was hard to get because we encountered an analytically intractable integral. Our regressive model, we model the density explicitly. GANs, they do it implicitly and don't bother modeling the distribution. And in VAEs, we derive the lower bound, which we maximize. And our regressive model, they do exact log likelihood maximization. And here we optimized our two-player adversarial loss. Inference, you pass it through a decoder. And here in the autoregressive model, you have to generate 1 pixel at a time. And here, same as VAE, you have no encoder, and you just pass Z to the generator. So sampling is fast for VAEs and GANs, but slow for autoregressive models because you need to keep conditioning on the past information. And sampling quality is often blurry and smooth in VAEs, but GANs sharp. It's very sharp. And autoregressive models, the sample quality is good, but like I said, the inference is very slow. And training is stable for VAEs and autoregressive models, and tends to be unstable for GANs. Has the homeworks come out yet? No. So you are going to implement in the homework the VAEs and GANs. So you want to teach yourself. Oftentimes you learn by implementing things, and I think you're going to learn a lot from the homework. And main weakness is it tends to create blurry images, and sampling is slow here, and there's a mode collapse, so the variability of the generated outcome might be not so great. And the takeaways, autoregressive models they use basically probability chain rule and use the models to predict a pixel given all the past. And pixel CNN makes a compromise, and as opposed to conditioning on all the past, it only conditions on however many the kernel size allows in CNN. And GANs, they do everything implicitly, and they don't bother trying to model the data distribution directly. And for optimal discriminator, GANs minimize negative log 4 of 2 times JSD between real distribution and fake distribution. And when the two distributions match, the optimality is at negative log 4. And these days, autoregressive modeling remains central in language models, like we saw. And GANs were dominant in 2014, 15, 16, 17. But these days, diffusion models have taken over for image modeling. But the central trade-offs still matter, likelihood versus sampling quality versus sampling speed. And we will cover diffusion models, I don't know when, but maybe in several lectures. All right, that's it for today's lecture. Thanks.